Welcome to Isel Engineering YouTube channel. I am Engineer Kidana Maran. Today I will show you how to model, analysis, design and prepare detailed drawing for strap footing shown on the screen using the following data. From ETABS analysis output data, we have this data that is for the corner or the eccentric column. We have a dead load of 300 kilonewton and a live load of 200 kilonewton. And for the center column, we have a dead load of 400 kilonewton and a live load of 250 kilonewton. From geotechnical data or from the soil data, we have a bring capacity of soil to be 200 kilonewton per meter square, and the permissible settlement is 25 millimeter, and factor of safety is 3. And from this geotechnical data, we can calculate very important data, that is the soil subgrade modulus, that is calculated as bring capacity of soil times factor of safety divided by the allowable settlement. So from this formula, I have to get our soil subgrade modulus to be calculated like this. Watch this video up to the end, since the last point I have tell you is a game changer. Subscribe my channel and share this video to structural engineers, site supervisors, contractors, civil engineering instructors and students, to clients who need structural design. Let's dive into this important design. First of all, I want to tell you some important points about strap footing. A strap footing are useful when one footing is eccentric and it needs to be connected with adjacent center footing by beam. It's better to open SAFE software, that is version 21, and start today's tutorial, that is how to model, analysis, design and detail your strap footing. So first of all, it's better to go to a new model. After that, the new model initialization box is coming like this. So after this, it's better to use built-in setting with. So after this, you have to correct all this data. Display unit, it's better to use a metric SI. So regions for default material. I have to use error code. So from this, I have to select error code. But in your case, you can select any building code of a standard in case of your region or location. So here in Ethiopia, I have to use error code because Ethiopian building code of standard is similar with that of error code. So after defining the region, it's better to define the other data. Still section database. Still section database is not important here because we have going to define, or we have going to design our reinforced concrete structure. But in case you can use error code. Still design code, that is for your reinforcement design. You can use error code for 2004. And for your concrete design code, it's better to use error code also. Error code to 2004. After this, make it okay. A new model initialization box or a new model quick template is coming like this. After that, you have to define this data. So number of green line in X direction, that is 2, since we have 2 columns. So number of green line in Y direction, make it 1. After that, spacing of grid in X direction, that is the spacing between the 2 columns, that is 5 meters. The spacing between these 2 columns is 5 meters. That is a given data. So I have to define it as 5. And the spacing of grid in Y direction, you cannot change this data. So after this, you have to go to grid only, make it okay. Okay, after this, our grid spacing is coming like this. The distance between the 2 columns is 5 meters. After this, it's better to go to define your material property. That may be property of concrete and property of reinforcement bars. To do this, it's better to go to define menu. After that, material property. From here, our default material, that is C30 is coming like this. I don't modify this material because first of all I have to select our design code. From that design code, our material property for C30 is coming like this. All the material property is similar, so I don't touch this. But in case of your reinforcement bar, I have to modify this property to S500 grade. So our material type is a reward. That is good. So the only difference is that I have to modify this property. So unit per weight per unit volume, that is used as it is, but mass per unit volume. So it's calculated as 70 78. So I have to change this data. After that, the modulus of elasticity is also defined as like this. I have to change all this data. After that, design property data. So from here, our rebar is S500. So our grade is also S500. I will change this. After that, the minimum yield strength, that is Fy, you have changed this data by dividing your your rebar grade to factor of safety, that is 1.15. After that, you have to copy your data. So because it's similar with expected yield strength, that is Fy, so you have to copy this data to this. After that, the minimum tensile strength, that is FU, have to use your reinforcement grade, and expected tensile strength, that is similar with that of the minimum tensile strength or FU. So you have to use your reinforcement grade as it is. After that, make it okay. From here, I have defined your concrete and rebar or material property like this. After that, it's better to go to define section property. From here, to define your section property, it's better to go to section property. After that, define frame section. From here, you have to cancel all this data. You have to delete all this data by controlling shift. You can delete all this data by pressing the shift key and selecting all this because this is still data. So I have to delete all this data first. After that, you can define your beam. So to define your beam, go to add new property. From here, you have to use a concrete rectangular. After that, select concrete and select this. After this, I have to define your beam as a strap beam, that is 300 widths by 600 millimeter depth. So material type is C30. After that, the depth have to define this as, so the depth is 600 millimeter and the width is 300 millimeter. After this, you have to change the section type, that is the section is beam section. After that, have to modify some data also here, that is our reinforcement grade is S500. So concrete cover is 50 to the top and the bottom. So make it okay. After defining your beam, it's better to go to define your slab and stiffened column property. To do this, it's better to go to define section property, slab section. After that, you have to edit this property. So our slab is S500. For first design criteria or first trial, it's better to use slab thickness of 500. So our slab material is C30. After that, the modeling type is a shell tip. It's not shell tip. You have to change to shell thick because our slab thickness is greater than 200. So after this, you can use a stiffness modifier here. As I told it before, you can check other videos all about a stiffness modifier, but in our case I have not used stiffness modifier here. You can add some notes here also about the property data, that is type is slab. It's not slab, we have to change it to footing. After that, the thickness is 200, make it 500. After this, make it okay. So our slab is defined like this. From this, you can define also your stiffened column by add a copy of this property. So make it a stiffened a stiff column with 500 millimeter tabs. So you have to change only this as stiff. The other data is similar. Make it okay. After defining the material property and section property, it's better to go to define your soil property. To do this, go to define spring property. That is, I have tell more about what is a point spring, when we use it, and what about a line spring. Uh, you can check our last tutorial. After this, in our case, I have to use area spring, so I'm going to define your area springers. From here, go to add new property. So this is a soil 200, because our bring capacity is 200 kilonewton per meter square. That is given in the geotechnical data. So from here, it's better to modify your what is your subgrade modulus. Have check it, and have put this data, this very important data for your design. So our subgrade modulus is like this. Have calculated it before. So from this, you can don't miss click compression only. So make it okay. After this, I have defined all the important data, that is material property, section property, and soil property. After this, it's better to go to model strap footing. It's better to go to kick draw area around the point. After that, for the first trial, you have to check your material. That may be the defined material, that is slab 500. After that, for the first trial, I will use 2000 by 2000 footing thickness. So I have to go to draw this. After that, it's better to go to draw your stiffened column. To do this, I have to change your material to as stiffened column. After that, the material or the stiffened column dimension to the x direction is 300 by 400, that is 500, that is given in your ETABS output. After that, I have to draw the stiffened collar like this. In our case, this footing is eccentric, so I will show it on the given data. This column is center and this column is eccentric from the given data. You have to correct your modeling. To do this, it's better to go to your safe. After that, click on your footing. So you have to go to edit. After this, move joint frame or shell. After that, I have to move your centric footing to the face of the column. To do this, our modeling footing that you have to model has a dimension of 2 meter by 2 meters. So the half is 2 divided by 1, that is 1 meter, and we have subtract also this, or we have subtract also this column dimension, that is the half of the column dimension, that is 300 millimeter divided by 2, that is 150. When we change it to meter, have to get 1.15. So you have to minimize our footing, or you have to move your footing toward this to get a face of the colon. So make it okay. After this, I have to move your footing toward this, but the footing dimension is so large. Starting from the face of the colon, it's better to minimize your footing here. So to minimize some dimension or some thickness towards this, I have to select at the corner point. After that, right click here. So go to geometry. So from the geometry, starting from your center, your x dimension is given as 3.15. So I have to add some similar data, that is 0.05, to shift your footing towards the x direction. So make it okay. After that, our footing is shift like this. In similar way, you have to check at this point also. So after this, our model of your footing looks like this. So it's similar with the given data. So after this, you have to save your modeling. Go to file, save as. So strap. I have one strap footing design, that is from here model. You have to save your data as strap footing design too. Make it okay. After this, your model is saved like this. After we have finished your model, it's better to go to assign all the load and soil data. To do this, first it's better to assign our soil data. To assign soil data, select your slab. After that, go to assign shell. After this, you have to select your defined soil, that is go to area spring. After that, select soil 200 that we have defined before. Make it okay. After this, the soil data is assigned to your model footing like this. After modeling your strap footing, it's better to go to define your load and load combination and assign your load plus your soil data. To do this, I have to first define all your load combinations. To do this, first you have to define your load pattern or load case. Our load pattern are data in live as it's given in your design parameter. So the self-weight multiplier is 1 and 0 respectively for data in the live load. After that, go to define load combination. You have to define two load combination, that is for service and ultimate limit state. For first combo is combo one, that is for service. So for service, it's better to define with a scale factor 1 1. So our data in the live load is defined as like this for service load. Make it okay. And second combination is uh, a combination for the ultimate, that is for a design of reinforcement. So in our case, I have to use error code. So error code load combination is 1.25 tail load and 1.5 live load. But in our case here in Ethiopia, it's better to use 1.35 for tail load and 1.5 for live load. But in case of Indian code, we can also use 1.5 for both dead and live load. That is a scale factor. So make it okay. After defining all the data and modeling your strap footing, it's better to go to assign the soil data and the load. After that, it's better to go to analysis and design. So first of all, it's better to go to assign your soil property. To do this, it's better to go to select all your slab. After that, go to assign shale area spring. From here, you have to select the soil data that you have to define before. After assigning the soil data, it's better to go to assign all the loads. To do this, first, it's better to go to draw. After that, draw a joint object from this point and this point. So after that, it's better to go to assign all the load. From here, your corner column have 300 kilonewton dead load and 200 kilonewton live load. From here, you have to assign this load to your corner footing. To do this, select the center. After that, go to assign joint load force. After that, date, make it 300 to the negative or to the vertical direction. After that, don't miss, you have to put your size of load for a punching shear, that is the column size. To get a punching shear design, so the column to the x direction is 300 millimeter and to the y direction is 500 millimeter. Make it okay. So the dead load is assigned like this. In similar way, you have to assign your live load, that is 200 to the face column. Have to change as live. Make it okay. The other load for the center column is 400 day load and 250 live load. If you have movement, you can also assign in similar way. So go to force, that is 400, which is a dead load. So you cannot movement in x and y direction here if you have a moment. So you have to use a similar size of load for a punching shear. Make it okay. So the dead load is assigned like this. After that, you have to assign your 150 live load in similar way. Make it okay. After this, it's better to go to analysis and design. So analysis, run analysis and design. The software itself go to analysis and design here. So our analysis and design is finished like this. From here, it's better to go to check three basic pointers, that is the punching shear, the deflection, and the soil pressure. It's better to go to check your soil pressure. To do this, go to display, show force or stress diagram, soil pressure. From here, select your service load combination, make it okay. After that, your soil pressure is 442.85. That is greater than your level bearing capacity, that is 200 kilonewton. And your it's better to check your punching shear. So the design for punching shear is less than one. That is safe. I have uploaded a video all about punching shear in design of math foundation. It's better to go to that tutorial and check more about all about the punching shear design mean. But in our case, it is less than one, so it's good. After that, our soil pressure is failed, so it's better to go to unlock and add some thickness or beam. So to do this, I have draw our beam. So go to draw. So select your beam that you have to define. After that, draw your beam like this, show in 3D. Our beam looks like this. Total, the trap beam is and the trap footing detail looks like this. Go to plan. So after this, it's better to go to design, run analysis and design. So go to analysis, run analysis and design, and check the data again. From here, go to display, show force, soil pressure. So our soil pressure is 206.32. It is averagely equal to that of the allowable soil pressure, but it must be below that level. You have to, it's better to add some area of footing. So really it's equal. I will pass here. So, but in your case, in real time design, you must uh, check that your soil pressure must be less than that of the level brain capacity. So in our case, it's better to proceed to the detailing. So to do this, go to make it unlock your model. After that, it's better to go to draw your strips because I have to going to design or I have to going to detail your reinforcements using a 1 meter or a unit width. So to do this, it's better to go to draw design strip. After this, you have to correct this data to 1 meter. This is because your footing is 2 meter by 2 meter and the half is 1 meter. So I have to change this data to 1 meter. After that, you have to draw your column and strip to the X direction. To do this, click on this point and the last point. So I have to draw your grid to the X direction. After that, it's better to change the layer strip layer to B. After that, you have to draw towards the Y direction like this. Sorry. You can draw like this. After drawing your strips like this, it's better to go to run analysis and design. After that, go to display, show show slab design. After this, it's better to use a strip method or strip based. So the top and the bottom reinforcement is shown. So you have to use a unit weights. Make it okay. After that, the maximum top reinforcement area is 350.12, and the bottom reinforcement area is given us 965.82 as like this. So you can use all this data also by using this area of reinforcement. You can change it to spacing and the number of reinforcement. It's simple. Go back to my math reinforcement design. I have do all the detailings, so you can check that tutorial. But it's simple. You can use this reinforcement area for this footing and this footing. So the maximum and the minimum reinforcement area is given at each point also. So you can divide it to the area of reinforcement that you have to use. So you have to get a total number of reinforcement. After this, the slab design and the detailing is finished like this. I will go back to your beam design, that is strap beam design. So to do this, it's better to go to display. After that, you have to show concrete beam design. So design type longitudinal rebar, that is uh, total. So make it okay. After this, I have to get a maximum top that is 930 and a maximum bottom that is 1598. So you have to divide it this to your reinforcement to your number of or area of reinforcement that you have to use, and you have to get a total number of reinforcement. I will show for the bottom reinforcement. So if I have to use diameter of 16, so area of reinforcement for diameter of 60 is 201 200.1, that is pi d square over 4. So you have to divide to this, you get total area of reinforcement for the bottom is 1598. So that is 1598 divided by area of reinforcement, that is 60. So to the bottom, it's better to use 8 number of reinforcement, that is 8 diameter of 60. So you can calculate all your area of reinforcement like this. These were the most important point regarding to model analysis, design, and detailing of strap footing. I hope this video is helpful for you. Please like this video and subscribe my channel to get new updates daily. See you in the next important video. Thank you for watching.